This is the first day. Let me say where we're headed because it makes today make sense. The far goal is to read real mathematics, the kind physics is written in, and not feel locked out. Today is the ground floor of that. The language for talking about collections of things, the language for precise reasoning, and enough algebra in the fingers that it never gets in the way. Sets, then logic, then a short algebra warm-up. And I'm not just going to teach the ideas. I'm going to actually solve every problem out loud, so by the end the work is genuinely done. Let's start with the most basic word of all after the break. Forget notation for a second. Picture a box. I can drop things into it. A 2, a 4, an apple, the number pi, another box even. Once something's inside, the box records only one thing about it, that it's a member, not its order, not how many times it went in. A set remembers membership and nothing else. That's really all a set is, a box that only remembers what's inside it. Two consequences fall out of that, and they trip people up forever if they're not said out loud now. First, order doesn't matter. Second, repeats don't count. Dropping the same 2 in twice changes nothing, it was already in. So the same numbers, in a different order or with something repeated, are not two different sets. They're the same set wearing different clothes. Hold on to that because in a few minutes it's going to save you. One more piece of vocabulary. When something is inside a set, we say it's a member or an element. That's it. Being in the box. And one last thing before the problems, because we'll keep reaching for the same few collections all day. They're not new, you already know them. The counting numbers, 1, 2, 3, and up. In this book they start at 1, not 0. Remember that. Then the integers, the counting numbers, their negatives, and 0. Then the fractions, called the rationals. Then every number on the line with no gaps, the reals. 4 names for collections you've known since school. That's the entire cast. Quiet question before we go on. If I show you the same 3 numbers in a different order and ask, same set or different set? Same set. Good. Keep that reflex. Everything else today rests on it. Now let's use it. Here's the one new thing, and it's just a shorthand. Instead of listing a set's members, I can hand you a rule that decides who's a member. Think of it as a machine. On the left, what kind of thing I'm feeding in. On the right, the test it has to pass. My job is to run the machine and see what lands in the tray. We'll do 6 of these. The odd-numbered ones from the first exercise set. And we are not learning 6 ideas. We're running this one machine 6 times. Problem 1. The set of 5x minus 1, where x is any integer. So I feed integers in. 0 gives minus 1, 1 gives 4, 2 gives 9, and here's the beginner trap I want to catch before I fall in it. Integers include the negatives. So minus 1 gives minus 6, minus 2 gives minus 11, and the outputs march off to the left as well. So the answer is, and so on, minus 11, minus 6, minus 1, 4, 9, 14, and onward in both directions, in steps of 5. Both directions of that ... are doing real work. Forgetting the left half is the number 1 mistake here. Problem 3. The set of integers x with x greater than or equal to minus 2 and x strictly less than 7. Watch the 2 ends. Minus 2 is greater than or equal, so it's allowed in. 7 is strictly less than, so it's out. I stop at 6. So the answer is the 9 numbers, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and 6. Problem 5. The set of real numbers x with x squared equal to 3. Now I'm allowed answers that aren't whole. What times itself is 3? The square root of 3. And that's exactly half right, which is the point. Squaring destroys the minus sign, so the negative root works just as well. So the answer is two numbers, the square root of 3 and minus the square root of 3. Problem 7. The set of real numbers x with x squared plus 5x equal to minus 6. I move everything to one side so it equals 0, then find two numbers that multiply to 6 and add to 5, 2 and 3. So it factors, and the solutions are minus 2 and minus 3. Quick sanity check by feel. Minus 2 and minus 3 multiply to positive 6 and add to minus 5. Matches. So the answer is the set containing minus 3 and minus 2. Problem 9. The set of real numbers x, where the sign of pi times x equals 0. This looks like a trig problem, and that's the trap. When is a sign equal to 0? At every whole step along its wave. So this is only true when x is an integer, which means this scary-looking set is secretly just which real numbers happen to be integers. So the answer is all the integers, every one of them. A trig costume on a very simple idea. Problem 11. The set of integers x whose absolute value is less than 5, that is, whose distance from 0 is under 5. So everything strictly inside the window from minus 5 to 5. And the one people forget, 0 is in, because its distance from 0 is 0, comfortably under 5. So the answer is the 9 numbers, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and 4. Step back. 6 problems, 1 machine. Read the input, run the rule, collect the tray. And stay honest about the 2 places it bites, negatives and both signs of a square root. Quick breath. We can describe a set 2 ways now, as a list or as a rule. Next question is a level up. Given a set, what smaller sets live inside it? We'll do all 8 problems from the subset exercise. Picture packing a bag. For each item on the table, I make one decision. Take it or leave it. A subset is just one possible packing. Some of the items, maybe all, maybe none. And because every item is an independent yes or no, counting is easy. 2 choices per item, multiplied together. So a set with n items has 2 to the n subsets. I compute that number first every time as a safety net. If my list doesn't hit it, I've dropped one or invented one. And 2 packings are always free, taking nothing and taking everything. But first, the single most important distinction in this whole chapter, and I'm slowing all the way down. Picture 2 things. On the left, an empty bag, nothing in it. On the right, a bag with one thing inside, and that one thing is itself an empty bag. Those are not the same. One is empty. The other is not empty. It contains exactly one item. The empty set has 0 elements. The set whose only element is the empty set has 1 element. If you blur those 2, sets feel like nonsense for months. So let it land. Now the reps. Problem 1. List all subsets of the set 1, 2, 3, 4. 4 items, so 16 subsets. I'll go by size so I don't lose my place. Size 0, the empty set. Size 1, the 4 singletons, just 1, just 2, just 3, just 4. Size 2, the 6 pairs, 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. Size 3, the 4 triples. Drop one element each time. 2, 3, 4. 1, 3, 4. 1, 2, 4. 1, 2, 3. And size 4, all of them. 1, 2, 3, 4. That's 1 plus 4 plus 6 plus 4 plus 1. 16. Confirmed. Problem 2. List all subsets of the set containing 1, 2, and the empty set. 3 items, so 8 subsets. And here the distinction earns its keep. The empty set, the empty set. The 3 singletons, the set containing just 1, the set containing just 2, and the set whose only element is the empty set. The 3 pairs, 1 and 2, 1 together with the empty set, 2 together with the empty set, and all 3 together, 1, 2, and the empty set. 8. Notice, one of those subsets is take nothing, and a different one is take the empty set item. They look almost the same, and they are completely different choices. Problem 3. List all subsets of the set whose only element is the empty set. 1 item, so 2 subsets. The empty set and the set whose only element is the empty set. Just those 2. Problem 4. List all subsets of the set containing the empty set and the set containing the empty set. 2 items, so 4 subsets. The empty set, the set containing just the empty set, the set whose only element is the set containing the empty set, and the set containing both of those. And notice the braces piling up. Every time I take an item into a bag, it keeps its own braces and the bag adds a new pair around it. The braces aren't decoration, they record how deeply something is nested. Problem 5. List all subsets of the set with 3 elements. The empty set, the set containing the empty set, and the set containing that. This nesting gets dizzying, so I'll name them. Call the empty set A, call the set containing the empty set B, and call the set containing B, C. Now it's just a 3-item table, 8 subsets. The empty set, just A, just B, just C, A and B, A and C, B and C, and all 3, A, B, and C. Then I only reinflate the names at the very end. Problem 6. List all subsets of the set containing the reals, the rationals, and the naturals. 3 items, 8 subsets. The empty set, the 3 singletons, just the reals, just the rationals, just the naturals. The 3 pairs, reals and rationals, reals and naturals, rationals and naturals, and all 3 together. And a deliberate trap. Yes, in real life, the naturals live inside the reals. Here that's irrelevant. I'm packing a table of 3 objects. Whether one secretly contains another is none of my business today. Problem 7. List all subsets of the set containing the reals, the rationals, the naturals, and the empty set. 4 items, 16 subsets by size. Size 0, the empty set. Size 1, just the reals, just the rationals, just the naturals, and the set whose only element is the empty set. Size 2, the 6 pairs. Reals and rationals, reals and naturals, reals and the empty set, rationals and naturals, rationals and the empty set, naturals and the empty set. Size 3, the 4 triples. Reals, rationals, naturals, reals, rationals, and the empty set, reals, naturals, and the empty set, rationals, naturals, and the empty set, and size 4, all of them together. 16, and watch it, the bare empty set as take nothing is a different subset from the singleton that took the empty set item. Both are in the list. Problem 8. List all subsets of the set whose 3 elements are the set 0, 1, the set 0, 1, 2, and the set 0. Refuse to look inside. Name them. A is the set 0, 1, B is the set 0, 1, 2, C is the set 0. 3-item table, 8 subsets. The empty set, just A, just B, just C, A and B, A and C, B and C, and all 3, A, B, and C. And yes, a take-one-item packing here ends up looking like double braces, because the item already had braces and the bag adds its own. If that looks wrong, sit with it until it looks right. So the pattern that retires this whole section. A subset is 1 yes or no per element, and there are always 2 to the n of them. We can build sets, read sets, and find the sets inside a set. One more set idea, and then we leave sets for the day. Combining a whole family of them. We'll do all 6 of these. 2 operations, and I'll anchor each to a feeling. Union. Pile everything together. You're in if you show up in at least one set. It reaches out. Intersection. Only the survivors. You're in if you're in every single set. It gets squeezed. Reach out, squeeze in. And the landmine I promised. Our counting numbers start at 1. That will change an answer in a minute. Problem 1. 4 small sets of letters. The first is A, B, D, E, G, F. The second, A, B, C, D. The third, B, D, A. The fourth, A, B, H. For the union, I sweep up every letter that appears anywhere, so the union is A, B, C, D, E, F, G, and H. For the intersection, I keep only letters in all 4. I test each. A is in all 4, yes. B is in all 4, yes. D is in the first 3, but the 4th set is A, B, H, so no D. D is out. Everything else is missing somewhere too, so the intersection is just A and B. Problem 2. 3 sets, each one just a plain list of integers from 0 through 24, and to be clear, these are listed sets that happen to include 0. This has nothing to do with where the counting numbers start. The first is the even numbers, the second the multiples of 3, the third the multiples of 4. Naming the pattern is the work. Union reaches out. The evens plus the multiples of 3 plus the multiples of 4, but the 4s are already even, and the even multiples of 3 are already even. So the only new arrivals are the odd multiples of 3. 3, 9, 15, 21. So the union is 0, 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, 21, 22, and 24. For the intersection, a number must be even, a multiple of 3, and a multiple of 4 all at once, which just means a multiple of 12 up to 24. So the intersection is 0, 12, and 24. Problem 3. For each counting number n, the set of whole numbers from 0 up to n. These stack like Russian dolls. Each contains the last and adds one more. Union reaches out to everything that ever appears. 0, 1, 2, 3, and on forever. All the whole numbers from 0 up. Intersection squeezes to what's in every doll, and the tightest doll is the very first one. And here's the landmine. Because our counting numbers start at 1, that first doll is the set 0, 1. So the intersection is 0 and 1. If we'd started at 0, the first doll would be smaller and the answer would shrink with it. Same problem, different convention, different answer. Problem 4. For each counting number n, the set of minus 2n, 0, and 2n. So minus 2, 0, 2, then minus 4, 0, 4, the flanks marching outward. Union grabs every even number, positive and negative, all the even integers. Intersection keeps only the point every set shares, the one that never moves, 0. Problem 5. For each counting number, the closed interval from it to one more. 1 to 2, 2 to 3, 3 to 4, end to end. Because they're closed, each interval ends exactly where the next begins, and that shared endpoint welds them. The union is one unbroken stretch, from 1 to infinity, including 1. The intersection? Neighbors share only that one endpoint, and a third interval further along leaves even it behind. Nothing sits in all of them, so the intersection is empty, and an empty answer is a real answer. Problem 6. Now the interval from 0 to 1 more than the number. 0 to 2, 0 to 3, 0 to 4, all pinned at 0, stretching right. These are nested. Union. The right end never stops, so everything from 0 to infinity, including 0. Intersection squeezes to the smallest interval, the first one. 0 to 2, both ends included. Here's the shape to remember. Union chases the largest. A nested intersection is trapped by the smallest. Keep that instinct, hunting the smallest object that still does the job, because you'll meet it again in the least upper bound, the supremum, the smallest number sitting above everything in the set. That's sets. Logic is the other half of the same wish, reasoning precise enough that you can't fool yourself. We'll put 5 statements into symbols and find the opposite of each. A statement is any sentence that's flatly true or false. We join them with a few connectors, each a feeling before a symbol. And, both must hold. Or is generous, one, the other, or both. Not, flip it. If then, a promise. If the first, the second is guaranteed. And the big two, for all, no matter which you pick. And there exists, at least one is out there. Now the payoff. Once a claim is in symbols, its opposite comes from a crank with 3 teeth. For all flips to there exists. There exists flips to for all. And the one nobody guesses, the opposite of if P then Q, is P happened and Q failed anyway. The arrow shatters into an and. To break a promise, you need one case where the condition held and the result didn't. 1. Every integer is even or odd. Every is a for all. For all integers n is even or odd. Crank it. For all becomes there exists, and the or flips to and. There exists an integer that's neither even nor odd. Notice it's false. No such integer, which is right since the original was true. 2. There's a real number whose square is 2. There exists a real x with x squared equal to 2. Crank it. There exists becomes for all. Equals becomes not equal. For every real x, x squared is not 2. 3. If a number is divisible by 4, then it's even, a for all around a promise. For all integers n, if 4 divides n, 2 divides n. Crank it. For all becomes there exists, and the promise shatters into p and not q. There exists an integer divisible by 4 that isn't even. False, of course, but the machine got me there without cleverness. 4. Every real number has an additive inverse. 2 quantifiers, and order matters. For all real x, there exists a real y with x plus y equal to 0. Crank left to right, in place. For all becomes there exists. There exists becomes for all, the inside negates. There exists an x such that for all y, x plus y is not 0. It now claims some number can't be cancelled by anything, and I got there without understanding it. That's the power of the crank. 5. Some student passed every exam. There exists a student S such that for every exam E, S passed E. This one shows why we never trust plain English. Crank it. There exists becomes for all becomes there exists, passed becomes didn't pass. For every student, there exists an exam they failed. In plain words, every student failed at least one exam. Ask most people for the opposite, and they say, no student passed anything. Wrong. Translate first, crank second, then read it back. Different gear. That was understanding. This is fingers. Pure fluency. 15 quick items, each with its answer. 2 things to hold. Multiplying out and factoring are the same door in opposite directions, so I can always check a factor by expanding it back. And completing the square is one fixed recipe. 5 to expand. X plus 3 times x minus 5 is x squared minus 2x minus 15. 2x minus 1 times x plus 4 is 2x squared plus 7x minus 4. X plus 2 squared is x squared plus 4x plus 4, and the middle term is there because 2 pairs meet in the middle. It is not just the 2 ends squared. 3x minus 2 times 3x plus 2 is 9x squared minus 4. The matched signs collapse it to a difference of squares. And x minus 1 times the quantity x squared plus x plus 1 telescopes down to x cubed minus 1. 5 to factor, the same door backwards. X squared minus 9 is x minus 3 times x plus 3. X squared plus 7x plus 12 is x plus 3 times x plus 4. X squared minus 5x plus 6 is x minus 2 times x minus 3. 2x squared plus 5x minus 3 is 2x minus 1 times x plus 3. And x cubed minus 4x, pull out the common x first, is x times x minus 2 times x plus 2. 5 to complete the square. The recipe every time. Take half the number in front of x, square it, add then subtract it. X squared plus 6x plus 5 becomes x plus 3 squared minus 4. X squared minus 4x plus 1 becomes x minus 2 squared minus 3. X squared plus 3x, don't flinch at the fraction, becomes x plus 3 halves squared minus 9 quarters. X squared minus 10x plus 30 becomes x minus 5 squared plus 5. And the one with the coefficient out front, 2x squared plus 8x plus 5, factor the 2 out of the x terms first, complete the square inside, then distribute back. It becomes 2 times the quantity x plus 2 squared minus 3. 15 for 15, every one checkable by expanding it back. Here's the whole day in 4 sentences. What I actually want to survive the next 3 weeks. A set written as a rule. Run the rule, keep what passes. List all subsets. Yes or no on each item, and expect 2 to the n of them. And an empty bag is not the same as a bag holding an empty bag. Union reaches out to the largest. Intersection is squeezed by the smallest. And to negate a statement, flip every for all and there exists, and turn if P then Q into P and not Q. The specific problems were never the point. They were practice for those 4.